Thank you, Devor, and thank you, Neil, for a wonderful presentation. So chips or integrated circuits are the enabling technology for every electronic device. They power everything. If you've got a phone with you today, you're holding 50 to maybe more chips. You've probably got 10 billion transistors in your pocket. It's just crazy how complex these things are. So today we're going to go on a quick journey through the world of chips. Some of you may already know what this machine in the background here is. For those that don't, we'll figure it out. I hope you'll learn something new. I also hope it inspires you to encourage younger people to study STEM, maybe chip design. And I'll say thanks to Neil Westy. He encouraged me way back when I was a high school student to do electronics. It's been a great and fulfilling career. So we'll go through what's a chip, how they're used, how they're made. We'll talk a little bit about the value chain, and then we'll talk about where Australia can participate. Finally, I'll give you an overview of what we're going to do at Macquarie University in this new Silicon Platforms Lab. So what's a chip? It's really just a miniature electronic circuit. So we've got transistors, we've got wiring, we've got capacitors, and we shrink it right down, and it goes onto a wafer. So on the left here, that's a silicon wafer with the chips built on it. Chips get packaged. Do I have a pointer? Oh, yeah. And so this is a package. So that essentially in this form is extending the pitch of the electronics on the chip. So you can put it on a printed circuit board. Printed circuit board's here, and then that goes into the end device. So when people talk about dice chips, that's these. When they talk about silicon wafers, that's this. And so where are they used? They're used everywhere. So a car is pretty much a computer on wheels. There's 1,000 chips in a modern car, used for the sensors, the safety systems, the motor control, absolutely everything. So when we had that time during COVID where we couldn't get cars, they couldn't get a few chips, and so then they couldn't produce the cars. In the phones, like I mentioned, there's so many integrated circuits from many suppliers, including Apple themselves. This is one of my favorite things to look at. It's a teardown of a Starlink terminal. This has got more than 400 microchips, and I think really integrated circuits make this system work. And so each of these little black dots is a chip that helps communicate with satellites going over your head at 1,000 kilometers away. So it creates an electronic beam that sweeps across the sky over about 5 minutes. And so you can see all of the microchips of these little black dots across the back. And on the other side are these flat panel phased array antennas. They're used in medical devices. So there's 2 chips in a continuous glucose meter. So one for wireless transfer and another one for taking the glucose reading. And so this is a disposable product. And then quantum. I think quantum's really, to commercialize it, it needs integrated circuits. So on the right here you can see an amazing 50-qubit computer from Google. And you can see all that wiring here, and David Riley actually gave a really great talk at a semiconductor event that the S3B put on at Morse Micro, and he talked about this. And all of that wiring is just to get access to the qubits at the bottom of the dilution refrigerator. And that needs to be replaced with another mechanism, and most likely integrated circuits will play a huge role in that. And finally, biotechnology. So the convergence between electronics and biotech is just beginning. This is a slide from a presentation at ITF 2024 at IMEC earlier this year. And this is talking about all the areas in which electronics and biotech will work together. So brain-computer interfaces, DNA on chip, lab on chip. And so this is also a fascinating area. And finally, in Australia, if you look at the list of critical technologies, most of these are built on advanced technology, and all of that requires integrated circuits. So if we want the best advanced technologies, I think we should get good at building the best chips. So let's talk about the types. So there's 2 main types of chips. There's the single element semiconductors, or the silicon-based chips, and that's the CMOS that Neil was talking about. And so that's 90% of the global market of chips. That's what TSMC predominantly makes. You get a lot of integration, so you get billions of transistors on a chip. The other technology is compound, so that's where you take 2 elements, gallium arsenide, indium phosphide, silicon carbide, and you put them together and you can make a really high-performance semiconductor. You get a little bit less integration, but it's great for applications in EV, in solar, RF, wireless technologies. The focus of our lab is silicon-based technologies. Macquarie University already has a really amazing research centre for gallium arsenide and gallium nitride. The MAD Lab, sponsored by Analog Devices, and so they focus on the compound semiconductors. And so there's probably ways that we'll figure out how to work together as well. So quickly, we'll just go into how they're made, and this will be a really brief primer. We showed the silicon wafer earlier. On the left here, you can see a cross-section of a chip. So down the bottom, you have the transistors, and then as you build up, you have the wiring, and as you get higher, the wiring gets bigger, basically. And so how's it made? Chip manufacturing is a really, well, at least CMOS chip manufacturing is a really complex process. So it takes 3 months, over 900 process steps, and you start with a really pure silicon wafer. So that's basically melted, purified sand. You put a seed wafer into it and you pull it out, then you slice it up to get the wafers, polish it to within a few atoms of thickness, of smoothness, and then we go through the cycle. And so we deposit some material, we apply resist, and really the hero of this is the lithography. So you might have heard about a company in the Netherlands called ASML. They make the world's most advanced EUV lithography machines. So the chip will go into that machine many times in the manufacturing process as we build up all of those layers. And so let's just go for a quick fly into this machine. So you can see it here. And so the way it generates the light is it puts droplets of tin into the air, and then it blows, it fires a CO2 laser at them with super high power. And it generates this 13.5 nanometer ultraviolet light. It goes through these very high performance mirrors onto a reflective mirror. So this is a reflective reticle that has the chip pattern on it. Then the light bounces down and it ends up on the resist layer that we'd put on earlier. So they prepare one wafer, get it all aligned, and then they image the other wafer as well. So they can push through about 180 wafers per hour, and they'll have multiple types of these machines in a fab. This machine costs about $200 million, and it's one of the most kind of complex machines, I think, that humans have ever built. And so here you can see it patterning the wafer. Okay, so the semiconductor value chain, it's made up of all the inputs, and this is a nice plot which came out of a study that the New South Wales government commissioned into the sector. We've got the inputs, which are the materials, the capital equipment, the design tools. You've got design and IP, fabrication, packaging and assembly. If you do all of these things, if you design, fabricate and assemble, you're an integrated device manufacturer. If you just design, you're a fabless chip company, and there's a lot of value in fabless chip companies. Majority of them fabricate with companies like TSMC or Global Foundries, SMIC. There's a bunch of chip fabs. But if you look at the numbers here, it's a huge value industry, and these are pretty old numbers from 2019, I think. So the design and IP market's a $100 billion market. The end market for chips is $4 trillion, and it's growing massively. Annual shipments, we make 400 to 500 billion chips per year. The market size, $600 billion in 2023, growing to 2.4 trillion in 34. And if you look at the tech companies, so I've taken the top 200 tech companies that are publicly listed, that have a valuation of more than $200 billion. So the total market cap here is 33 trillion. And then you say, which ones design chips? And this isn't even the foundries or the design software companies. This is just companies that design chips. And so that's by market cap more than half, and there's quite a lot of companies in there. So it's a huge industry. And you can notice that there's companies here that you might not think are chip manufacturers like Microsoft or Apple, but they actually make their own chips to make their products better. All right, so what are the trends in the industry? First thing is this, and this is pretty amazing. So 90 nanometer CMOS, back in early 2000s, had about 1 to 2 million transistors per square millimeter. The latest technology from TSMC has over 300 million transistors per square millimeter. So that's just fascinating. That's driving the complexity and the performance of these systems. That's why you can put a kind of command into ChatGPT and it'll give you back a reasonably good answer. With these this number of transistors, you've got this increasing cost because it's obviously a much more complex system. It takes a lot more time to design and verify. So this is showing the cost to do an advanced system on chip in different technologies, starting at 65 nanometer, going all the way to 5 nanometer. So something's got to change here. We can't spend $500 million making a system on chip anymore. And if you look in here, it's not even just the design, it's all the verification and software that you need on top of it. You know, when you've got 2 billion transistors, there's a lot of stuff to check. And you don't want to get it wrong because it costs a lot of money to manufacture it. The other trend is advanced packaging. So companies like AMD and Xilinx have been using advanced packaging for the last 10 years. So it's not new, but it's new to applications outside of CPUs and GPUs, which is great. Advanced packaging just means we're putting different types of chips together in a heterogeneous or advanced package, and we're doing that so that we can reduce the power consumption or improve the performance. So if I kind of summarize all the stuff that we think is interesting, or the general trends, we start with transistor density. So when you've got a lot of transistors, you try and do as much as you can in digital. So these really complicated RF front ends are going to fall away, and we're going to do much simpler front ends and do some more compensation in digital. We've got the advanced packaging, we've got the increasing costs, which means we want to simplify or maybe make smaller chips. We've got the other part that's very interesting to us is kind of AI or ML-driven verification and design. I think there's going to be like a fundamental change in the design tools for chips over the next kind of 5 to 10 years, which mean that you can do a lot more with a lot less designers, which will help reduce the cost. And finally, the market's a really great and growing market. So we actually have a lot of really cool companies in Australia that make or design chips. I'll put some of them here. I'm sorry if I've missed you, but we've got, you know, several startups. We've got some established startups. We've got some new ones. We've got design centers. So we do chips here, but we can do more. And these are my thoughts, how we can increase the participation. But the main areas we can think about are the inputs to the process, or the design, or the manufacturing. I think design sits front and center. It's very low cost. It's not low cost, but it's not that much to create a company to design chips compared to building a fab. And I think the design of chips will drive the requirements in the other areas like manufacturing or the inputs. So if I draw like a diagonal up here, the things that are interesting to me are design and IP, the design tools and methodologies, and then some advanced packaging. If we wanted to build a bunch of fabs, maybe a non-leading edge fab would be interesting in CMOS, like a mature tech, and there might be some work we can do in compound. And then I think on the inputs, given Australia's resources in mining, we can probably do a little bit more there as well. Okay, how are we going for time? We good? All right, so now I'd like to introduce the Silicon Platforms Lab that we're setting up here at Macquarie University. I'd like to thank Dan Johnson, the Macquarie team. It's been a long road and we got there, so it's been great, thank you. Now we get to do the real work. So like Neil said, Macquarie's actually got a really great pedigree in chip design. So David Scallon and Neil Westy were here in the 90s. Neil had the 60 gigahertz project, the Mad Labs here, and now we're building a silicon-based design team. We're bringing industry into the university. It's really hard to do chips without industry experience. So like Neil said, we're trying to bring the best and brightest in. So we've got Neil and David as adjunct professors, and so we're really grateful for their support. And then we're bringing industry staff in. So we've got Rickard, who's joined us from Sweden, had great roles at Ericsson, Nokia, a really great cellular architect. And we're doing the same for these kind of leading roles. So head of digital, head of hardware, head of analog mixed signal engineering. That really help when we're training the next generation of engineers as well. We've got 7 positions open, so we're looking for all of these roles, as well as masters and PhD students. And our focus areas are as follows. So we are interested in communications and sensing, how we make use of chiplets and advanced packaging to do that a little better than we do it today, and then how we can use software to design those systems and make them a little more efficient. So we want to do more with less. We want to train engineers for industry. If we're going to have a bigger chip industry in Australia, we need more people to work in it. And we'd like to also support research teams inside the university and the wider community to make chips. So if you've got a really interesting biotechnology project or a quantum sensor and you need an integrated circuit to make that work, we want to help you. We're going to have a base level of core IP that'll be available to researchers and research groups, and we're going to make it quick and easy so you don't have to start from scratch when you're building a chip. Why now? I think I covered the first point. Critical technology and defence rely on them. It's a good entry point with this new kind of mode of building chips using heterogeneous integration. We're very excited to work with Ben and the team at the AMRF on the phase 2 project they're building out there, the Advanced Semiconductor Manufacturing Plant, so that'll be exciting. How to work with us, I mentioned that. Thank you.